Hello, and welcome to Frost Sullivan's Growth Webinar. Today, we explore the critical megatrends reshaping the battery materials landscape. We'll delve into how innovations in anodes, cathodes, and binders are not just enhancing performance, but are pivotal in building a more secure, sustainable, and resilient energy storage supply chain for the future. The global push for electrification, from EVs to consumer electronics and stationary storage, is creating unprecedented demand for advanced batteries. However, this growth is constrained by supply chain vulnerabilities, geopolitical tensions, and the physical limitations of current materials. Organizations are navigating a landscape defined by the concentration of critical raw materials, evolving regulations like PFAS restrictions, and the urgent need for higher energy density and improved safety. Against this backdrop, material innovation is emerging as the most critical path towards scalable, cost-efficient, and high-performance energy storage. Frost & Sullivan's ongoing research highlights the rapid evolution of this sector. The shift is underscored by the urgency. Organizations can no longer rely solely on incremental improvements to established lithium-ion chemistries. They need new materials and processes that overcome supply chain bottlenecks, mitigate regulatory risks, and deliver a step change in performance for diverse applications. And that's where next-generation battery materials enter the picture. Traditional lithium-ion batteries, powered by graphite anodes and NMC or LFP cathodes, have dominated the market but are approaching their performance limits and face significant supply chain and regulatory challenges. New material technologies do not replace these overnight. Instead, they extend and enhance the possibilities. Innovations like silicon anodes, Prussian blue cathodes for sodium-ion batteries, and dry electrode processing are filling the gaps that current chemistries cannot address. Over time, as these technologies mature, they will increasingly converge with market needs, creating a more diverse and fit-for-purpose battery ecosystem. In the near term, multiple chemistries will coexist. Longer term, the convergence of new materials, sustainable processing, and supply chain resilience signals a fundamental reshaping of the broader battery market. One of the most meaningful insights from the discussion is that supply chain security and scalability, not just performance, are the real barriers and opportunities for new technologies. Most battery supply chains are heavily concentrated in specific geographies, with over 75% of battery production and 95% of graphite anode processing occurring in China. This creates vulnerability to geopolitical disruption and price volatility. Furthermore, mining projects for critical minerals like lithium and nickel are increasingly facing social and regulatory pushback, jeopardizing raw material availability. Modern battery material innovations address this by leveraging alternative, more abundant elements. Silicon anodes, utilizing silicon, the second most abundant element on Earth, to reduce dependency on Chinese graphite and offer a tenfold increase in lithium-ion storage capacity. Sodium-ion batteries, using Prussian blue analogs made from common feedstocks like ammonia and natural gas, eliminating dependency on lithium, cobalt, and nickel. Localized production. Companies are strategically scaling production in Europe and the US, supported by regional policies and grants, to build independent and resilient supply chains. This multi-pronged approach ensures that even with fragmented global supply chains, advanced batteries can be produced without being solely dependent on a single region. The guidance is clear. Develop technologies that are not only high-performing, but also inherently secure and scalable from a raw material perspective. Partnerships play a critical role here, particularly between material innovators, battery manufacturers, and OEMs to ensure alignment and commitment across the value chain. Regulation is rapidly becoming a core driver of material innovation in the battery space. Organizations are adapting to new rules that govern not just the end of life of batteries, but the very materials used within them. Key regulatory trends include PFAS restrictions, driving R&D into PFAS-free binders, particularly for cathodes, with a shift towards water-based and bio-based alternatives. Battery passport and recycling quotas, emphasizing the need for easy-to-dismantle designs, creating opportunities for debondable and resealable adhesives. Critical Raw Materials Act and FEOC rules, incentivizing supply chain localization and reducing dependence on foreign entities of concern. Right to repair and eco-design laws, pushing for user-replaceable batteries, influencing pack design and material choices. These regulations are compelling a strategic shift. However, they can also be a double-edged sword. While they provide funding and support for local sustainable projects, the regulatory process itself can be slow and risk impeding the rapid scaling needed. The philosophy is one of proactive adaptation. Leading material companies are not just reacting to regulations, but are actively participating in EU substitution groups and Horizon projects to develop the next generation of compliant materials. Battery material innovation is increasingly recognized not only for improving energy density, but also for enabling broader strategic business goals. Its impact shows up in several key areas. 1. Market creation for new electronics. Silicon anodes enable smaller, more powerful batteries for next-generation wearables, smart rings, and augmented reality glasses, powering the AI and fitness tracking revolutions. 2. Supply chain resilience. Sodium-ion batteries and silicon anodes diversify the raw material base, reducing exposure to lithium price volatility and geopolitical risks associated with graphite, cobalt, and nickel. 3. Cost competitiveness and stability. Chemistries based on abundant materials, sodium silicon, offer a more predictable and stable cost structure for downstream producers. 4. Sustainability and safety. New chemistries like sodium ion virtually eliminate thermal runaway risks, while dry processing removes toxic solvents like NMP, making production safer and more energy efficient. Innovation shifts the industry away from a one-size-fits-all approach towards a diverse ecosystem of fit-for-purpose technologies. With rising performance demands and complex supply chains, this diversification is no longer optional, it's essential. Battery material innovation thrives within deeply interconnected and collaborative ecosystems. 3 partnership categories are emerging as foundational. Technology and material partners, silicon anode, sodium-ion cathode, and advanced binder companies provide the core innovations that enable performance and supply chain leaps. Battery manufacturers and OEMs. Their application needs dictate performance requirements, e.g., cost versus energy density for urban EVs, and are critical for scaling and commercializing new technologies. Research and regulatory bodies. Participation in joint projects and advisory groups ensures new materials are compliant and aligned with regional strategic goals. Together, these partnerships support a more integrated, resilient, and innovative approach, reducing time to market, de-risking scale-up, and creating a more balanced global supply chain. Battery material innovation is evolving into a powerful strategic enabler for the entire electrification ecosystem. By combining advanced chemistries like silicon and sodium-ion, sustainable and scalable production processes like dry electrode, and a collaborative approach to supply chain resilience, organizations can overcome performance plateaus, unlock new markets, and build a secure energy future. This concludes today's growth webinar. To dive deeper, we invite you to explore Frost & Sullivan's full research on the battery materials market. Thank you for joining us, and we look forward to bringing you more insights on transformational growth.